Hello APC Mechanics students, in Unit 6 Oscillations, Class 6, 6.1 Simple Harmonic Motion, Vertical Oscillator, Part 2. In today's video we're gonna solve some exercises to what we have explained so far. Now let's start by exercise 1. Students in the lab construct the mass spring oscillator shown in the figure. Using a single spring and attaching objects with different masses, they collect the data in the table. Which of the following graphs has the correct best fit line and can be used to determine the spring constant of the spring? So if you consider the shape of the curve, so we're talking about straight line, which is linear, then we're talking about linearization. The period of vertical or horizontal oscillator is given by 2 pi square root m over k. Then if we do the linearization, we're interested in plotting t square as function of m. So that would be 4 pi square over k multiplied by m, and the slope in this case is given by 4 pi square over k. Then we can directly eliminate a, c, and b, and d would be the correct answer because the straight line of the best fit almost passes through or equidistant, or the points are closest to this straight line. Then D is the correct answer. Now exercise 2. A student puts a vertical block spring system in motion by pulling down on the block and then giving the block a quick push upward. A motion sensor placed under the moving block produces the graph of velocity v as function of time t shown above. Which of the following gives the best estimate of the frequency of the motion of the block and the block maximum displacement from equilibrium? Here let me mention something very important. We can plot versus time three variables of motions, x, v, and a. These three variables of motion, they have the same period, so the period can be determined from the xt graph, from the vt graph, from the at graph. Now let's determine the period. The period represents 4 amplitudes. Now this is an amplitude, so let me say this is 0.1, that's 0.2, that's 0.3, so this is 0.4, 0.5, and that would be 0.6. Now one amplitude corresponds to 0.6 minus 0.2, which is basically 0.4 seconds. And if we're interested in the period which corresponds to 4 amplitudes, that would be 1.6 seconds. Now the frequency is given by 1 over the period, which is 1 over 0.6, and that would be almost 0.625 Hertz. Then we're limited to B or D. Now we need the maximum amplitude. This is a VT graph. We can determine the maximum velocity. The maximum velocity is given by 15 centimeters, but we know that this is also equal to omega xm. Then xm is given by Vm divided by omega, and that would be 15 centimeters divided by omega. Omega is 2 pi f, which is 2 pi over the period. Then the period is given by 2 pi divided by, which is 2 pi over the period, and the period is 1.6, so that would be 2 pi divided by 1.6. Plugging that on the calculator, we would find that almost xm is given by 3.82 centimeters. Why centimeters? Because the speed is in centimeters per second, and the closest to that would be 4 centimeters, making B to be the correct answer. Now systems A and B containing identical springs and identical blocks that can slide along a surface of negligible friction. In system A, the surface is horizontal. In system B, the surface makes an angle theta with the horizontal. Initially both the blocks are at rest and in equilibrium. Each block is then pulled at the same distance t in the direction shown in the figures and released from rest at t is equal to 0. The block in system A is being pulled a distance d horizontally. The block in system B is being pulled the same distance d along the ramp. and we have no friction, then both blocks will perform simple harmonic motion. For system A, when the block is halfway between its release position and its equilibrium position, the block's kinetic energy is K and elastic potential energy of the spring block system is U. The ratio K is over U. Now they're ignoring system B, they're talking only about system A. This happens because sometimes on the paper itself such given is related to several questions. Now we're interested in system A. We need to find the ratio K over U when the block is halfway between the equilibrium and the amplitude. Now K over U, K is the kinetic energy, which is half mv square, and U is the elastic potential energy. Now in order to do the cancellation effect and to have an answer is independent on the variables of motion and the physical quantities, we need to approach the problem differently. Let's think about the energy. Since this is a simple harmonic oscillator, the energy is given by half mv square plus half kx square. Now it would be difficult if we consider the general form, so it's better if you think about energy in the terms of half k a square, and in this case a is the amplitude, which is d square. And also let me write that this is equal to k plus us. So k indeed can be expressed in terms of half kd square and us. Now half kd square equals to k plus us, and we're interested in determining the kinetic energy in terms of these. Then the kinetic energy would be given by half kd square minus us. So that would be equal to what? To half kd square, which represents the total mechanical energy, minus us, or u over u. Now u depends on the position. About which position we're talking? We're talking about the position midway between equilibrium and amplitude, which is basically d over 2. So that would be half kd square minus half k d over 2 square over half k d over 2 square. Now half with half would cancel, k with k would cancel, d square with d square would cancel. We're left with 1 minus 1 over 4 over 1 over 4, which is basically 3 over 4 over 1 over 4, and that would be 3. And this is not a straightforward result, which makes E to be the correct answer. What do we benefit from this? So if you think about it, k over u is equal to 3, which means k is equal to 3u. Then midway between the equilibrium position and the amplitude, the energy stored in the form of kinetic energy or contained in the system is 3 times the elastic potential energy stored in the spring. Okay, so equity here, so if you think about it, that midway between equilibrium and amplitude, that the energies are shared 50-50, that's wrong, because the functions aren't linear. We're talking about quadratic functions. Kinetic energy will have 3 times the potential energy elastic. And if the mechanical energy of the system E in total is 4 joules, then midway the kinetic energy would be 3 joules and the elastic potential energy would be 1 joule. Systems A and B for exercise 4, we have the same given. Now I will skip these. After the block in system A is released from rest, after it's being pulled by a distance d, which is the amplitude. Now this is the amplitude y because we released it from rest. No initial velocity is given. The time for the block to reach a maximum speed is given by delta Ta. So you can think about delta Ta is 1 over 4 the period, because the maximum speed is attained for the equilibrium and we're moving from the amplitude. After the block in system B is released, the time for the block to reach a maximum speed is given by what? So in other words, you can think about delta A to be a factor of the period. So if you are able to compare the period of systems A and B, so you would choose the correct answer out of these. Now we have said the period of a horizontal oscillator is given by 2 pi square root m over k, which is the same period for a vertical oscillator, but we didn't discuss throughout the course the period of an oscillator inclined on a ramp. Now the only thing here that has been changed is that we have a normal push, but the normal push doesn't affect our system because it's also present in the case of a horizontal oscillator. Now here we would have the pull of gravity, but not a complete pull of gravity. It would be modified and given by mg sine theta, which is a modified pull of gravity. Also, the normal push is a modified normal push, which is given by mg cosine theta. However, whether it's mg or mg sine theta, we can always implement a constraint equation and we would end up with the same differential equation and with the same variables or parameters of motion, and the period we would given by 2 pi square root m over k, which means the period for the system A is equal to the period of the system B, also which is equal to the system for a vertical oscillator. For this reason, if we're talking about delta TA, which is the time required to pass from the amplitude to the equilibrium position, which is a factor of the period, and the period is invariant, then A is the correct answer. Now exercise 5, two identical massless springs are hung from a horizontal support. A block of mass 1.2 kilograms is suspended from the pair of springs as shown above. When the block is in equilibrium, each spring is stretched an additional 0.15 meter. When the block is set into oscillation with amplitude A, it passes through the equilibrium point with a speed v. In which of the following cases will the block, when oscillating with amplitude A, also have a speed v when it passes through the equilibrium point? The block is hung from only one of the two springs. The block is hung from the same two springs, but the springs are connected in series rather than parallel. A 0.5 kg mass is attached to the block. So they're asking us which of the following would not affect the speed v when it passes through the equilibrium point. Now the speed v through the equilibrium point is given by the maximum speed, because at the equilibrium point the position is 0, and the maximum speed is given by omega xm. Xm is A, so that would be omega A. Knowing that A is not affected, so we're looking for how does this affect omega. Omega is given by the square root k over m. So anything that we do changes k or m, that would affect the speed. The block is hung from only one of the two springs, that would change k, because k would decrease, so that would affect omega overall, so we can directly eliminate one. The block is hung from the same two springs, but they are connected in series rather than in parallel, that would affect k, so we can directly eliminate 2. A 0.5 kg mass is attached to the block instead of 1.2. That would affect the mass, again affecting omega, so we can also eliminate 3, which means A is the correct answer. Now exercise 6, a block of mass capital M is suspended from two identical springs of negligible mass, a spring constant K and unstretched length L. First, one spring is attached to the end of the other spring, which means they are connected in series. The block is then attached to the end of the second spring and slowly lowered to its equilibrium position. The two springs stretch a total distance of x1. 2L represent the length of the two springs freely with no mass m attached. We added the plus x1 because this is the elongation when we connect the mass m. Next, the springs are hung side by side. The block is attached to the end of the springs and again slowly lowered to its equilibrium position. The springs each stretch a distance of x2 as shown in figure 2 above. Which of the following equations correctly shows the relationship between x1 and x2? When they are connected in parallel, each spring is given by L and elongation would be x2. We need to find the relation between x1 and x2, and this can be done by considering the equilibrium condition. If you consider figure 1, what are the forces that are acting on the block? We have mg downward, and this should be equated by k multiplied by x1. Why we didn't consider 2L? Because this is only the elongation of the spring. This is the first equation that we can set. Now, but k here, you should pay attention that k is the equivalent stiffness of the first spring and the second spring. So let me say this is k prime. They are connected in series. If each spring is of stiffness k, then k prime can be determined by the reciprocal sum, which is 1 over k prime, 1 over k plus 1 over k, and that would be 2 over k. then k prime is k over 2. Then the equation is given by mg k over 2 multiplied by x1. This is the first equation. Now the second equation would be mg equated by Hooke's law, the force on by the springs. Now these two can be replaced by a single spring of stiffness k double prime x2. Now they are connected in parallel, so that would be the usual sum. K double prime would be k plus k, which is 2k. Then mg is equal to 2k multiplied by x2. Now let's do the first equation over the second equation, then 1 over 2. That would be mg, which is k over 2 x1 over mg over 2k x2. Now mg with mg would cancel, k with k would cancel. We would have 1 over 1 is equal to x1 over 2 over x2 multiplied by 2. Then that would be 1 is equal to x1 over 4x2, taking 4 up, which means x1 is equal to 4x2, making D to be the correct answer. Now exercise 7, an unstretched idle spring hangs vertically from a fixed support. A 0.4 kg object is then attached to the lower end of the spring. The object is pulled down to a distance of 0.35 meters below the unstretched position and released from rest at time t is equal to 0. Because it's being pulled from the equilibrium position and it's not given initial velocity, so this is the amplitude. Now a graph of the subsequent vertical position of the lower end of the spring as function of t is given above, where y is equal to 0 when the spring was initially unstretched. What is the spring constant of the spring? Now we're interested in k. K can be determined whenever we know the mass and we know the period. So basically the period is given by 2 pi square root m over k, which means period square is equal to 4 pi square m over k, which means m is equal to k, we're interested in k. K is given by 4 pi square m over period square. Now k is given by, now here we're not interested in the amplitude, 4 pi square. The mass is given by 0.4. Now what about the period? Now this, okay, the period, it's apparent that it is 1 second because this is an amplitude 2, 3, 4, so 1 second. Now plugging that on the calculator, the value of k is given by 29. Let me double check. So the value of k is given by 16, almost 15.79 newtons per meter, which is almost 16 newtons per meter, making A to be the correct answer. Now a student designs an experiment to verify dependence of the mass m of an object attached to a spring on the period t for an oscillating vertical spring object system. The student attaches a hanger to a spring, places weights on the hanger, pulls the hanger down, releases it from rest, and measures the corresponding period of oscillation for the hanger. However, during data entry, the student neglects to add the mass of the hanger to the values of the attached masses for the spring. The student constructs a graph for the data to determine if the data agrees with the equation t is 2 pi square root m over k, where k equals to the elastic constant of spring. Which of the following graphs best represent the student's recorded data? Now, because we're plotting t as function of m, we know that for a function given by y is equal to a square root x, it should look something like that. Okay. Now, because we're plotting the period, not the period square, so we can eliminate this and that. Now, this is a parabola open up. We can also ignore this and we're left with C. And because the graph didn't start from the origin, this might be due to an experimental error, or simply because the student neglects to add the mass of the hanger to the values of the attached masses. But basically C, it's the closest to this curve. The graph shown above represents the displacement as function of time for an object with mass 3 kg attached to an idle spring. The spring has been stretched and released at time 0, allowing the object to oscillate about its equilibrium position. Calculate the total mechanical energy of the system. We know that the mechanical energy of the system has 3 different forms. The general one, and the 2 specific one related to kinetic and elastic. So that would be half m Vm square, also equal to half k a square, where a is the amplitude or xm. Now because this is the displacement time, we're gonna use this one, but first we need to determine the stiffness. Now the period is given by 2 pi square root m over k. Now t square is equal to 4 pi square m over k. Or if we know the period, okay, so fine, let's determine it this way. 4 pi square m over k, then k is given by 4 pi square the mass, which is 3, divided by the period square. Now the period is determined by 4 amplitudes. This is 1, 2, 3, 4, basically 2 minus 0, which is 2 seconds, 2 to the power 2, and the value of k can be determined, and it's almost given by 29.6 newtons meter, and that would be half 29.6 multiplied by a. The amplitude is given by 10 centimeters, which is 0.1 square. Plugging that on the calculator, then we find that the mechanical energy of the system, it's almost given by 0.148, and that would be 0.15 joules, making D to be the correct answer. Exercise 10, as an exit ticket for today's video, a student designs an experiment to study the period of oscillation for an object on a spring. The student measures the mass of a sphere as m. The sphere is hung at equilibrium from 2 parallel springs that each have a spring constant of k. The student pulls the sphere down a distance a and releases it from rest. The student calculates an expected value and measures an experimental value for the period of oscillation. The experimental value, here we should be very careful, the experimental value of the period is less than the expected value because. Now, one way to think about the problem after reading it. So they're telling us why the experimental value of the period is less than the expected value, or you can think about it. Here we're trying to compare theoretical and experimental. So we're saying that the experimental is less than the theoretical. This is one. Another way to think about it is why the theoretical is greater than the experimental, and we're talking about the period. The period is given by 2 pi square root m over k. So basically the student must have done something theoretically which increases the value of the period. So let's investigate. Now, if you think about B, the student, or let me go by order. A, the student used the spring constant of 1 spring in calculating the period instead of 2. We know that the springs affect the period, so I will keep A. B, the student measured a smaller than actual value for A. A doesn't affect the period, we can directly eliminate B. The student measured a larger than actual value for A. We can directly eliminate it. The student measured a smaller than an actual value for m and used this value in calculating the period. We know that m affects the period. The student pushed the sphere a little at release. We know that initial velocity does not affect the period. However, it affects the amplitude and the maximum velocity. So we can directly eliminate A. We're left with A and D. Okay, let's check D. The student measured a smaller than actual value for m and used this value in calculating the period. You should understand that this is the part of the theoretical calculation. Why? Because the experimental value for the period, it's only about measuring the period using a stopwatch. It doesn't require the measurement of m nor the measurement of k. Period experimentally can be measured only via a stopwatch, but whenever we're talking about measuring the value of m and we have the value of k to determine the value of t, this is the theoretical part because we're using this formula. Now, at the beginning of the exercise, we mentioned that we're interested in finding the mistake that the student done in the theoretical part that increases the value of the period. Now, if the student measures a smaller value than than actual value for m, which means m decreases, which makes the period decreases. Okay, so this is not expected because we're interested in the experimental value of the period is less than the expected value, or the theoretical value is greater than the experimental value, so we can directly eliminate D. Now for A, the student used the spring constant of 1 spring in calculating the period. We know that in parallel grouping, the stiffness of the springs increases. So if we remove the 1 and we only use 1 spring, that would decrease the value of K. Decreasing the value of K means increasing the value of the period, because these are inversely proportional at some point, which means the period will be greater. And indeed this conforms or confirms the fact that the experimental value of the period would be less than the expected value. Then that's it for me in this video, guys. See you soon in a new one.